Hello everyone, my name is Kumar, and this is my implementation of scalable recognition with the vocabulary tree. So the first paper that I used to gain some inspiration for this is action recognition by dense trajectories. The basic premise for this method is that it uses dense trajectories sampled from each frame and uses displacement information from a dense optical flow field to track these trajectories. And then based on the results obtained, they label the action being performed. So the trajectories in a video are clustered and a transformation matrix is computed for each cluster. And then the elements of these matrices are used to represent trajectories by using SIF descriptors between two consecutive frames. So the main implementation that I have based this on is from the Scalable Recognition with the Vocabulary Tree by Hendrik Nister and Stu Venius. And the theory behind this is that we extract SIF features and then we hierarchically quantize these in a vocabulary tree by using k-means clustering and allocate some weights and then use a TF-IDF scoring mechanism which allows for more efficient lookup of words, and then based on this scoring and we find out uh, where each node is and we find the relevant image in the database. So the idea behind SIFT feature extraction is that there's a bunch of descriptive points and then which can be extracted to provide a feature description. So in this implementation, I have used the open source library OpenSIFT, and it's widely recognized as a good SIFT library, and I have used this to extract the SIFT features to build the vocabulary tree. So as mentioned before, the vocabulary tree can be constructed using hierarchical k-means clustering on a set of SIF descriptor vectors. The construction of the tree is completed recursively by first creating the SIF descriptors, then training contained in a node into k parts, and then getting k clusters. The training data is partitioned into uh, k groups where each group consists of descriptor vectors closest to a particular cluster center, and accordingly the original node will have k children. A mapping is required to support necessary image retrieval between each leaf node, and each of the leaf node has to record its unique mapping relation, which is the frequency of the center descriptor to a certain image's descriptors. This mapping is implemented in the inverted file on which the TF-IDF scoring will be performed on. So once the quantization is defined, the definition is necessary of the relevance of a database image to the query image based on how similar the path is down the vocabulary tree. So for each node, we assign a weight wi according to the formula given in the slide, where n is the number of images in the database and ni is the number of images with at least one descriptor vector path to node I. Then we score it based on the second formula, and this is how we can find the relevance of the query image in the database. To measure performance, we query the database with every image in it and calculate the accuracy of the result to the query image and then see how accurate it is. So in this, we used 4 images as the 4 best results from the algorithm. Then we say it's 100% accurate if the 4 matches come from the same node or same cluster. So I used the Microsoft Cats and Dogs database for the images, but only the cats images loaded up due to system constraints. And there's a 90% chance when the branch factor is 5 and only 50 images were used as the training data. And there's a gradual decline in accuracy when the database becomes bigger, as it drops to around 70% when 500 images are used. So in conclusion, this is a good algorithm. It could potentially be used internet-wide as a image search engine, and yeah, I see good potential with this. Thanks for your time.